For most of human history, materials were defined by what they were made of. Gold behaves like gold because it is made of gold atoms. Diamond is hard because carbon atoms arrange themselves in a specific crystal structure. The chemistry determines the properties, or so we thought. Over the past few decades, physicists discovered something remarkable. A material's behavior doesn't always come from the atoms themselves. Sometimes it comes from the way those atoms, or even larger structures, are arranged. And once scientists realized this, they began creating materials that appeared to violate common sense. Materials that bend light backwards. Materials that remain in motion without thermal equilibrium. Materials that conduct electricity with zero resistance. Materials that appear to possess negative mass. None of these violate physics. Yet all of them challenge our intuition. The reason copper conducts electricity while glass does not has little to do with the atoms themselves. The answer lies in quantum mechanics. Inside solids, electrons occupy energy bands. In conductors, electrons can move freely through these bands. In insulators, they cannot. This framework, known as band theory, explains much of modern materials science. For decades, physicists believed the properties of materials emerged primarily from chemistry. Then researchers began asking a different question. What if structure itself could become the material? This is where the science gets genuinely interesting. Normally, light bends when entering a material because the material changes the speed at which electromagnetic waves propagate. This effect is measured by a quantity known as the refractive index. In ordinary materials, the refractive index is positive. In 1968, Soviet physicist Viktor Veselago asked a strange theoretical question. What if a material had a negative refractive index? Such a material would bend light in the opposite direction. At the time, this seemed impossible. No naturally occurring material possessed such properties. Then, decades later, engineers built microscopic structures smaller than the wavelength of light itself. The result was the first practical metamaterials. Their unusual behavior came not from chemistry, but from geometry. This is a major scientific point many scientists have missed. Metamaterials are essentially programmed matter. In 2012, Frank Wilczek proposed a new phase of matter. Ordinary crystals repeat patterns in space. A diamond repeats the same atomic arrangement over and over. Wilczek wondered whether a system could repeat in time instead. The idea was controversial. Many physicists initially believed it was impossible. But in 2016, experimental groups created systems that exhibited behavior consistent with what are now called time crystals. These systems oscillate at stable frequencies despite being driven periodically. The key insight is that time crystals break a symmetry known as discrete time translation symmetry. That sounds technical, but the idea is simple. The system develops its own rhythm that differs from the rhythm driving it. This is not perpetual motion. Energy still enters the system. Physics remains intact. Yet a completely new state of matter emerges. Zero resistance is where most explanations stop. In physics, that's only the beginning. In 1911, Heike Kamerlingh Onnes cooled mercury to just 4 degrees above absolute zero. Its electrical resistance vanished, not decreased, vanished. Decades later, physicists discovered why. Electrons normally repel one another. Inside a superconductor, they form pairs known as Cooper pairs. These pairs move collectively through the crystal lattice. Instead of scattering off atoms and generating heat, they travel coherently as a quantum state. This is why superconductors exhibit exactly zero electrical resistance. This phenomenon is also responsible for the Meissner effect, in which magnetic fields are expelled from the material. That is why superconductors can levitate magnets. Negative mass remains hypothetical. No confirmed example of true negative mass has ever been observed. However, researchers have created systems whose effective behavior resembles negative mass. In 2017, physicists working with ultra-cold atoms demonstrated conditions under which atomic clouds responded to forces as though they possessed negative effective mass. The distinction matters. Physicists are not claiming to have discovered exotic matter. Instead, they engineered a system that behaves mathematically like negative mass under specific conditions. This is an important theme in modern material science. For thousands of years, humans searched for new substances. Today, physicists are doing something different. They are designing entirely new forms of matter. Matter whose properties emerge not from what it is made of, but from information, geometry, symmetry, and quantum mechanics. That shift may prove to be just as world-changing as the discovery of steel, electricity, or the transistor. Except this time, we're not just discovering matter. We're learning how to design reality itself.